Welcome to the second video all about inclined planes. Here we're going to go over the basic strategy, which is not terribly dissimilar from our other strategies of applying Newton's second law. And then more importantly, we're going to tackle an example problem to work out how to solve one of these types of calculations. All right. So first, part A, just the strategy. Whenever you have a math-based inclined plane problem, something on a ramp, something on a hill, on a freeway, on a loading dock that's tilted, all right, our strategy when applying Newton's second law is really quite the same as any other strategy for applying Newton's second law. The first step is to draw a free body diagram. This shows all the forces acting on the object, and it shows what direction. So we'll know which of those forces are going to be present, which of those pieces we'll need to include when we do like the sum of the forces. And also it will show us that direction so we can tell if we have to break any forces down into their components using trigonometry. So that's the purpose and value of those free body diagrams. Step 2, we want to make sure we make it clear what our positive and negative directions are. Last time we saw this, it was almost too obvious, right? You say up is positive, to the right is positive usually. But now there's extra meaning and importance behind step 2 because we're often going to be tilting our axes. Instead of having x and y, we're not going to do that anymore. We're going to tilt along that incline with x prime and y prime. You don't have to put the prime if you want, but that's just me emphasizing that they're different. So we might say down the ramp is the positive direction. You don't have to. And perpendicular up from the ramp is the positive direction. Okay. I know in calculus, I think just from other student works I've seen in previous years, you don't technically rotate your coordinate like this, but you actually rotate your free body diagram and then approach it that way. That's totally fine. But then make sure you're showing me that free body diagram. If you have no idea what I was just saying, we'll use this approach. All right. Step 3, we've seen this before. Any force that is not acting in our coordinates, now down the ramp and perpendicular to the ramp, we're going to break into the x prime piece and the y prime piece. Usually, the nice thing about using these coordinates is this is almost always just the weight of the object. So instead of breaking 2 or 3 forces down, we only have to break 1 down. And then lastly, we set up the sum of the forces in the x direction and the y direction. All right. When objects are moving down a ramp, they're not going to be like launched up from the ramp, nor will they be like crashing through the ramp like this. So usually, not always, but it's pretty rare, the sum of the forces in the y direction are always going to add up to be 0. That's not to say there aren't forces, but since it's not going to be flying off the ramp at this weird angle, you can set the sum of the forces in the y direction. Sometimes that's true for the x direction, sometimes it's not. It depends if it's moving and if it's accelerating. Okay, so there's our strategy. We learn by doing. So here's an example problem. It says I have a 4-kilogram crate and it is sitting at rest on a loading ramp. Here's my loading ramp. If the ramp has a 28-degree angle, so that's what this theta is right here. This is 28 degrees. All right, calculate the static friction that's keeping the crate at rest, and also find the normal force acting on the crate. Here we go. Feel free to hit pause if you want to try it on your own, or just watch and see how I approach it. Step 1, I'm going to draw a free body diagram. I know that weight is acting on that crate because we're here on Earth and there's always weight. There's a normal force. Normal force is perpendicular to the surface, so my surface is down the ramp. Perpendicular in this case is going to be kind of up and to the left. Tough to draw. Fn. It says there's a frictional force. Friction always acts parallel. Parallel is up and down the ramp. Normally, if you imagine it was on wheels or if it was frictionless, the crate would roll down this way. So there must be a static friction that's acting in the opposite direction. That would be, I'm going to go F sub S. There are no other forces acting on the crate. Okay, there it is. There is my step 1. My step 2, setting up my positive and negative and my coordinates. I'm not going to use our traditional x and y. I'm going to say that down the ramp, so down and to the left. Aha. That's my new x. You could call it x prime if you want. And then perpendicular to that, that's my new y. And I usually like having down the ramp as positive because that's the direction it would go if it could slide down. And then up and perpendicular, I'll say as positive, but that doesn't matter so much. Okay. Step 3, breaking forces into components. The normal force I do not have to break down because it is acting in the exact same direction as y prime. My frictional force, while it is acting in the opposite direction, it's acting like this. That's just in the negative direction. So I don't have to break that one down. I'll just put it in as a negative since I'm saying down the ramp is plus. However, I do have to break down the weight. So here I go. I'm going to draw the original vector. And then my tip from the last video, so we know exactly where our theta is to immediately after drawing the straight down, draw the y component. And the y component from my coordinate system is up and to the left. So this is FW. This piece here, this is FW in the y direction. And that means this angle here is theta. That's my 28 degrees. I proved it in the last video. Down the ramp is this one, FWX. And remember, these are still at 90 degrees, so I can still use my sines and cosines. Looking at FW, here's the hypotenuse of the triangle. Okay, here is the side that's adjacent to theta. This is a little different. Now my y-coordinate is adjacent to theta, which means that when I write it out, FWY, that's equal to that hypotenuse times the cosine of theta. And FWX, it's now the opposite. The sine, if I wanted to write it out, that's op over hyp, opposite over hypotenuse. That's equal to FWX, because that is opposite, divided by the hypotenuse, which is FW. That's my quick proof that FWX is equal to FW sine of theta. That's exactly what I would write right here. FW sine of theta. Okay, this is just my scratch work to figure that out. Write it down by all means if you need to. Okay, step 4. Now I'm going to set up my sums of the forces, Newton's second law, in order to solve for these two things, static friction and the normal force. I could either do the sum of the forces in the x direction or the y direction. You can kind of pick. Let's start by writing out the sum of the forces in the x direction. While you weren't looking, I hit pause and I quickly copied these things over so I have the same thing. But here we go. I'm going to use blue. Okay, I'm on step 4, setting up Newton's second law. Let's look at the sum of the forces in the x direction. And technically it's the new x direction. All right, again, you don't have to put that little prime symbol. What is acting in the x direction? The frictional force is acting in the opposite x direction. So I might have an opposite Fs. And anything acting down the ramp? Yeah, this piece here. This component, Fwx. That is acting down the ramp. So Fwx down the ramp, which was what I called the positive, minus Fs, that equals ma. This is the acceleration down the ramp. Well, it says the box is at rest. So that means the acceleration is 0. So this is 0. So Fwx equals the static friction. If I just swing this over. The first part of the question was asking for this value. It didn't ask for the coefficient. It just asked for this frictional force. That's Fwx. And I already said that right here. So that's Fw sine of theta is equal to Fs. Well, Fw, the weight, is always equal to mg. So that's mg sine of theta equals Fs. Plugging in, oh man, what was the mass of that cart? 4 kilograms. Jump back. So that's 4 kilograms. 4 times 9.8, that's G, times the sine of 28 degrees. That equals Fs. I punched that into my calculator, and hopefully I didn't make a mistake. When I punched in all those things, I got 18.4 newtons. You can email me anger if I did it wrong. That is the value of the frictional force. I'm not saying you have to show all these steps. Here are the crucial ones I should see on any test. Okay, this one, oh my gosh, absolutely. Okay, probably like this one. Or instead, you could do that one, so one of these or the other. And I should definitely see you plugging in and getting an answer. So at least show me that original equation. This is helpful, so I see that you know you're setting them equal to each other. And as usual, make sure you show me plugging in, and then the answer, duh. Okay, but I had this so it's nice and laid out. That is the frictional force. Let's solve for the second part of the problem. It was asking for the normal force acting on the box. So on my next slide, I'm kind of resetting. Okay, I got rid of all that work I had in the x direction. Now let's look at the sum of the forces in the y direction. If you're ever not sure, like, oh man, it's asking for the normal force, what do I do? We're pretty much always doing the same thing. We add up the forces in the x, and we add up the forces in the y. If you're not getting those values from either of those two things, well, maybe it's a trickier problem. All right? What forces are acting in the y direction? Well, the first one is the normal force. Remember, this is the new y direction, and that's perpendicular to that incline. So the normal force is, and if I say that up and to the left is positive, that would be a positive force. Any others? Yeah, this piece right here. It's acting down in the negative y prime direction, minus Fwy. Well, the box is not launching off that ramp or crashing through, so the sum of the forces equals ma, that equals 0. So the normal force is simply the y component of the weight. And I already did that. Right there. That's equal to Fw cosine of theta. That's equal to mg times the cosine of theta. The mass, it's still 4 kilograms. Times 9.8 times the cosine of 28 degrees. Punch that in your calculator. Make sure you are in degree mode. And what I got was 34.6 newtons. Make sure you do not think that the normal force simply equals mg. That is incorrect. In this case, the normal force is a component of the weight. This right here is only true if the object is not accelerating up or down and it's on a level surface. That's a very specific requirement. Anyway, nice. I solved for the frictional force as well as the normal force acting on that crate. Thanks very much.